Bismillah ar-Rahman ar-Rahim. Alright class, Assalamu alaikum and welcome back to EE 382, that is electromagnetic fields. This is the third lecture of week 1, so let's begin. While uploading the second lecture of this week, I came across the fact that at the very end of that lecture we had some text issues. The text was not clear enough, so and all apart from that, I also wanted to start the discussion of today's lecture by summing up whatever we have discussed in the last lecture, especially the last example of light field. So this would give us a very good summarization of whatever I want to convey to you throughout this week. All right, and I would like you all to consider the lectures of this week, that is the 3 lectures including this one, to be the necessary preliminaries of physics, which every student should know regardless of whether he or she is taking this course or not. These concepts of physics that we have discussed so far, or fields we have discussed so far, is not particularly related to electromagnetic fields. These are the concepts which are available even in mechanics and in a study of thermodynamic fields and so on and so forth. So all these discussions you will find nowhere in any book. Rather, this is the gist of whatever experience I have acquired while teaching this course for last 15 years. So I think that students do not find this subject relevant, or they get lost somewhere within this study, during the study of this very crucial course, is the fact that they don't even know, most of you don't even know these basics, which by the way you should have learned by now after completing your intermediate. But we all know that our approach in intermediate is mostly to pass with high marks. We don't unfortunately focus on building up the concept. So that's the reason why most of us, by most of us I mean 99.9% of the students, they don't have the concept of fields or these generic concepts that we are going to cover in this week at all. They don't have those concepts built at all. They know the definitions and all, but they don't know the exact concept of it. So this should be a big motivation for you, that whatever we are discussing here, whatever time you are spending here for this first week, 3 lectures, will not only build concepts for electromagnetic fields, but these concepts are generic for every type of study of physics every area of physics, I should say, like which I just named, like thermodynamics and like mechanics. Everything has got the same concepts. You should realize that by now we have talked a very little about or I think we haven't talked about electromagnetic fields so far, just a sentence few here and there, but not exactly about electromagnetic fields. Right now we are just discussing general concepts of field. Okay, so this should be a good motivation for you, that whatever your time is spending here, whatever time you're utilizing here, is not only giving you the prerequisites for electromagnetics, but also for whole of the physics. Right, so these fields, the scalar field, vector field, time dependent, time independent, force field, flux, densities, fields and sources, all these concepts are generic. They are not particular to electromagnetic fields. All right, so this week should be regarded as the preliminary physics that each and every one of you should know in order to succeed in electromagnetic fields or any other field in which the concept of fields are involved. Secondly, the week number 2 should be regarded as the preliminary mathematical foundations of electromagnetic fields in particular, or in any area in which vector calculus or vector algebra is required. So now after this introductory remarks, let me give you the last example, and that would sum up the last example that we discussed in lecture number 2, and that would sum up the discussion of fields, and then we'll proceed on. And our target is to complete this lecture by today, inshallah. So what we said is that consider a black box, black room, completely black, no wall, no windows, no doors, no ceiling fan. Every wall and every the ceiling and the floor is colored black, no furniture at all. The only person or the only entity present in that room is you, and 100-watt, and for simplicity, monochromatic light source is present. That's it. So we have got a bounded region, number 1, and if the bulb is turned off, so this is just a 3-dimensional space, nothing is happening over there, no important event is taking place, so that space is just a 3-dimensional space and nothing more than that. But as soon as someone turns that light on, then what happens? This whole room, an event occurs that this whole room is now illuminated. Now there exists a light field. There exists a light field. Okay. So I'm writing it here, light field now exists here, right? Some event is taking place within a bounded region, so now it qualifies as a field. So we are giving it the name light field. All right. So one can argue that light, as soon as the bulb is turned on, the light field exists. All right. So what is the effect of this light field? You are present within this room. You will say that you can sense the intensity. Your eyes, which are the sensors, can sense the intensity of that light. If you are standing somewhere here, intensity of light will be higher. If you are standing somewhere here, the intensity of light will be lower. And if you are standing somewhere here, it will be even lower. So the effect of that light field is the intensity of light, which the sensor can sense, or what we call, when we are standing in the light, like in this room, how do we quantify that light? Do we say that this light is larger, or this light is smaller? No, we say that intensity of the light is higher, intensity of the light is smaller. We say, we use commonplace terms like the light is very dim. By that we mean the intensity of light is smaller. We say, if we say that the light is very sharp, it is very glaring, it means that intensity of the light is very large. So it is actually, the effect is the intensity of the light. The effect is something which the sensor can sense, and this sensor can sense the intensity of the light. This sensor can sense intensity of the light, and this sensors appreciate the presence of the light in terms of its intensity. So we can say that an intensity field has been established or can be defined, which is the function of x, y and z, which is the position. If you are standing here, it will be different. If you are standing here, it will be different. If you are standing here, it will be different, obviously. So excuse me. So this intensity field, which is the function of x, y and z, can be there are certain ways in which what we can do is we can take some sample points, some sufficient number of sample points, and using an intensity meter, a light intensity meter, which are commonly available in the market, we can just measure the intensity at certain sample points. And then there are mathematical ways which can take this sampled data and generate an expression which is a function of x, y, and z, which represents whole of the field, whole of the intensity field within this room. Just like we did with the experiment of the Ohm's law. So then I wrote some arbitrary expression. Let's say after applying those mathematical procedures using this sample data, we end up in this expression. Now this expression is representing whole of this field. Now if I want to find the field at this point, I don't need to take the intensity meter and turn the light on again and then measure it. No, I don't need that. I can just destroy this room and scrap everything away, and even then I can find that if I would need the intensity at this point, what would that be? Because I have the representative mathematical expression now. I can find intensity at any point I want within this room. The important thing is within this room, and the dimensions of this room are important, obviously, because if the room was bigger, this expression would be different. If the bulb is of let's say 10 watts, then the expression would be different. So I have got this expression for this particular setup in which we have got a certain dimensions room and 100 watts bulb. That's it. But we all know, okay, this is so this field is now intensity field, and if you replace the values of x, y, z, you will get a scalar quantity, as intensity should be a scalar field. So the intensity is a scalar field. This light field itself is not cannot classify this arrangement as the establishment of a scalar field or a vector field, because light is just an event that's going on within this boundary. What I mean by that is one can argue that when the bulb was turned on, the light is present here, the light is present here, the light is present here. The light is in fact present everywhere within this room. So it means that presence of light is just an event which is present everywhere within this room, right? But what is changing is the intensity of that light. The effect of that light is changing. So something, you can loosely say that something which is constant, the entity which is constant throughout, the existence of that quantity is, if existence of that quantity is constant throughout, then that quantity is not technically a field, that is, but that quantity is actually the event, right? So just like in the case of battlefield, there is a bounded region, battle is happening there, battle is happening everywhere in that battlefield, right? So what you can quantify is the valor, is the fear, rather than the battle, okay? Because one can argue, all right, let's be fanatic about it. All right, battlefield is there. This is the battlefield, let's say. All right, so one can argue that, okay, if two soldiers are fighting here, and two soldiers are fighting here, and two soldiers are fighting here, and two soldiers are fighting here, so at those points where the soldiers are fighting, yes, there is battle going on, and on the rest of the place where there are no soldiers, there is no battle. That's wrong, because where two soldiers are fighting, that at that point, yes, the fighting is going on, but the battle is the collection of all those points where the fighting is going on, and battle is happening in a bigger region, right? So everyone will say that, okay, this is the battlefield. Same can be the case of wheat field. All right, some would say that wheat is growing on this point, and on this point, and on this point, but in the middle there is nothing happening. So why do we regard the collection of all these plants as a field? We say that this is the wheat field, यहाँ पर गंदम की फसल है, all right? Why don't we say that this is just one plant, two plant, three plant? No, irrespective of what is going on between these 2 points, collectively it is evident that wheat is being grown throughout this bounded region. Whatever is happening in between, is it of importance? No. Similarly, whatever is happening in between this empty space, even then you would say that battle is going on. Yeah, at this point fight is going on. At this point, fight between two soldiers is going on. But overall, what's going on? Battle is going on. Okay, so either the battle is going on throughout this region, or it is not going on. This is an event. This is itself is not is not an effect, right? Same is the case with this. Light is present everywhere. Okay, it's present everywhere. That's an event, that it's present. What is not an event is that intensity of this field is not constant everywhere. It is changing. So that should give you a difference between an event and the cause of that event. Okay, so we can say that light is an event, and it causes effect. So this is the cause and this is the effect. Cause and effect. So if the nature of effect defines that if the field is a scalar field or vector field. So why are we appending the word field with light? Good question. That will be clear in a minute, inshallah. All right, so we all know that every light source emits photons. Okay, and this photon has got a velocity. So if this light source is emitting photons everywhere, because light is everywhere, so photons are everywhere, and if I want to know the velocity of photon at every point, at this point, what I can do, I can take a photon velocity meter. There is a meter, let's say photon velocity meter, and I just take certain sufficient amount of sample points and then measure the velocity of the photons at every point, at every sample point, and then apply the mathematical procedures which I talked about. Then at the end of applying those mathematical procedures, I will get an expression of velocity of photons, which will be the function of x, y, and z. And since velocity is a scalar quantity, is a vector quantity, so we should expect certain unit vectors associated. Okay, I, j, and k. I'm sure you are familiar with this. These I, j, k, and unit vector in the direction of x, in the direction of y, in the direction of z. And I'm now writing some, arbitrary equations to give you an idea that you can get an expression something like this. So if although this expression was obtained from sample data, not from everywhere, but after applying those mathematical procedures, we have got an expression which is the representative of velocity of photons at every point within this field. Okay, so as long as there is the source is the same, and as long as the bounded region is the same, we can use this expression to find out the velocity of photons at any point we want within this room, within this three-dimensional space or field, okay, this bounded region. So for your reminder, you should know that there are infinite number of points within this this three-dimensional space, okay. You should know that. All right, so now this light, the event of the presence of light within this bounded region, it is defining an intensity field. If you are interested in intensity, our eyes are not capable of finding, you know, the velocity of photons, so we are not, maybe we human beings would not be interested in finding the velocity of photon at everywhere within this room, at every point within that room. But there might be some applications in which we might need the velocity of photon at every point within certain bounded region, so it might be possible. So this field is defining intensity field, if we are interested in intensity, and it is also defining a velocity of photons field, which is a vector quantity. So now this expression gives us a vector field, although the, you know, effect is the same, the cause is the same, sorry, light. So these are the effects: intensity field, vector field, okay, intensity field or velocity field. These are the effects, and there can be several other effects which we might be interested in, okay. There can be another example. Instead of, let's say this is the same room, instead of having a bulb here, this is a dark room filled with gas or normal air, the same room. But now if I remove the bulb from here, and if I attach a fan here, fan, let's say this fan consumes the power 100 watts now, then if this fan is turned off, nothing is important is going on here. But if we turn this fan on, there is no light now, this is just a fan. What will happen? This fan will blow air. So now there is air field within it, air field. You know that how air is felt by humans. This fan will pressurize the gas molecules within air. The fan will push the gas molecules from this point, from this point towards the other ends of the room. And if you are standing here, when those air molecules would hit you, you will feel that air is blowing. All right. So if you're here, you will feel that the pressure of the air is more. If you're here, you will feel that the pressure of the air is lesser. If you're here, then the pressure will be even lesser. So it means that there exists a pressure field within this room, because effect is what? Pressure. And the effect, the cause of that effect is air. So you are saying that now, after turning this fan on, there exists an air field, just like you said that after turning this bulb on, there exists a light field. But having air or having light is just an event, it is not a cause. Because one might argue that air will be here, will be here, will be here. Yes, air will be everywhere, but the pressure of the air will be different at every point. All right, so we can take again pressure at different points, and we can define a pressure field here, which will be the function of x, y, z. Okay, and we'll have certain expression which will end up in a scalar quantity. And by the way, we can also be interested in velocity of each air molecule which is reaching you at any point. So again, you can take different points and calculate or measure the velocity through a velocity meter, that what will be the velocity of the light, of the air molecules, and you can apply those mathematical procedures, and you will be ending up in a velocity expression which will be obviously different. So I just came up with another example for fields for you. So pressure field, and you can also get a velocity field for this air. Now this air is offering you a scalar field, which is a pressure field, and a vector field. So whatever this air, this cause of the field, just like this light was the cause of the field, whatever this air is offering you as an effect, as effects, the collection of all those effects, right? We have got a velocity field here, the pressure field here. The collection of all those fields will be regarded as air field, although existence of air is an event, mind you. It is an event, not a field. But why are we keep referring this to as an air field or this as a light field? Because the collection of all fields, all the effects which this light is offering you, those effects can be regarded as field. So in general, we can say that we can collectively take these effects and knowing that these effects are actually the fields, so we append the word field here. Although the existence of light within this room is an event, not a field, but this event is producing causes, which causes give you effect. So we say, okay, there exists a light field, okay, there exists air field. Okay, I hope things would be clearer now. So this was the physical definition of fields, which we talked about in very much details. What is the mathematical definition of field? Mathematical definition of field is that field is a function of position vector, and this is pretty much clear over here, that there we have got a function which is the function of position, right? Here also we have got a function which has got which is a function of, we have got a variable, an effect, which is a function of position. So field is a function of position vector, means that field is a function which has got the variables x, y, and z, and these x, y, and z are position coordinates. All right, so physical definition we talked about in great detail, and mathematical definition is field is a function of position vector. So wherever you get a function which is of a variable which is a function of x, y, and z, that is position, then it means that that function is actually a field. And if that function is a vector function, then the field is a vector field. If the function is a scalar function, then the function is the scalar field. All right, so if this source is changing, obviously there will be change in the field. If the source is time dependent, then the field will also be time dependent. This is what we have talked about earlier. Now let's move on quickly because we are running out of time. Force field and flux density field. So if a field like light field offers, you know, a vector field, if the light field offers an effect which is a vector field, that effect or that vector effect can be further classified into a force field effect or flux density effect. If there is a sense of any movement in a vector field, then that vector field belongs to a category of vectors which is known as flux density. So this velocity has got belongs to this velocity vector belongs to a special category of vector fields which is known as flux density type of field. If there is a sense of force, if there is a sense of force in a vector field, right, then that vector field can be regarded as the force field. And generally we, in order to completely categorize or define or explore a field, we try to find all types of effects which are associated with that field. Like we will try to find the scalar field, a scalar effect of that field. We will try to find the vector effect of that field, and not only the vector effect, we will try to find the force field type of vector effect of this field. We will try to find the flux density type of vector effect of that field. So this is really important to know. If there is availability of each of flux density type vector field, then we will try to find that. It is not necessary that we must find a field, must find an effect which belongs to flux density or field or force field type of vector field. So we will, in order to classify a field completely, we should try to find its scalar effects, its vector effect, and within this vector effect we should find out the force field effects and the flux density effect. So flux density, again, if the effect has got a sense of movement, like velocity means something is moving, right? So this velocity belongs to a special category of the vector fields which is known as flux density type of vector field. And if there is a sense of force, nothing is moving, but you there is an application of force on some object or on some charge or something like this, in that case we'll say that that vector field belongs to force field type of vector field. So sources and fields, we have talked about fields in great details. I just want to emphasize here that whenever there is a field, there is a source. Whenever there is a field, there is a source. Whenever there is a field, there is a source. Without any source, there is no field. You should remember that. So if the field is time dependent, by the way, then there should be some function of time as well. Some variable of time should also be appended in all these expressions, but right now we are considering that the field is time independent. So fundamental physical quantities, you should know that fundamental physical quantities are like mass, energy, right, charge. So mass is something which occupies a space, right? And I'm not going to discuss what kilogram is and what how the length meter is standardized and all those things are given in your book. So I'm not interested in that. I just want to know, just want to convey or remind you that there are certain fundamental quantities like mass, like energy, like charge. Mass is something that occupies a space, and space is something which is measured in meters. Energy is something which enables some entity to apply force, and force is measured in Newton. Remember that whenever there is energy, there is a tendency of applying force. Or you can say that if something or some entity is applying force, meaning that it has got some energy within it, either kinetic energy, potential energy, or any type of energy. But energy and force are both related. Remember that. Whether you are working in mechanics or you're working in electromagnetic fields, you should remember that wherever there is force, there is energy. Wherever there is energy, there is an innate capability to apply force, and force is measured in Newtons. Charge is a fundamental quantity. You all know that, but often students confuse charge with electrons, which is not true. So that's not true. Okay, that electron is not charge. Charge is a fundamental quantity which is on electron, and you should know the value of that as well. You should know that how much coulomb of charge is present on electron. But mind you, electron is not charge. Charge is some entity which resides on electron. Proton is not charge. Proton carries an equal amount of charge which electron carries, but of opposite nature, which is positive, and that charge is on the proton. Proton itself is not a charge. Okay, because charge does not carry any weight. Secondly, you should know that like charges repel each other. You all know that. Dislike charges attract each other. So these are the things you should know. But now let's come here. Electric field, magnetic field, and electromagnetic field. So far in 2 classes we just discussed about this term. Now let's try to elaborate on this. Electric field, you should expect, just like light field, some field which has a bounded region in which some electrical effect is present. That's all. That is known as electric field. Okay, and that electric is the event. Okay, this is actually this electric is a cause which will give you what? Which will give you several effects, vector effects and scalar effects, and collection of all those effects in terms of mathematical expression as a function of position, collection of all those effects which will be defined as the fields. Throughout this course we will try to explore those fields. Collection of all those fields are known as electric field. So whenever there is electric field, there is some source associated with it. Okay, there is some source associated with it. Then magnetic field, there should be some source of magnetic field. All right, so let's talk about gravitational field first, because you all know that you can all relate to that field. Wherever there, according to Newton's law, wherever there is a huge mass, there exists a gravitational field surrounding this, and which was given by G, m1 m2 upon r square and all. Okay, I don't exactly remember the denominator, but if this is Earth, a huge mass is present, then there exists a field, a bounded region, in which there is a capability of pulling other masses towards it, and we call that as a gravitational field. That field is gravitational field. Okay, so gravity is the cause of several effects. Gravity is the cause of several effects. Like if we have a mass here, 1 kilograms, this mass will be attracted to this Earth by a force. It means that force is the effect of gravity. If there was no gravity field, this mass would not experience any force. So again, if we take several masses on different points sample points and try to find the force at each point. Then there are mathematical ways which will give us a force field which will be a function of x, y, z, and again, because this is a vector quantity, force is a vector quantity, we all know, so we should expect some I, j's and k's. Okay, so I'm just writing arbitrary, values here. Let's say we have got this expression. Let's say this is not true. Okay, so this gravitational field is providing an effect which is force, that if you bring another mass within this field, it will be attracted by this. Okay, just in the case of light field, your eyes were capable of sensing the effect of that light field. In this case, your eyes are not capable of sensing the effect of gravity. You cannot see gravity falling around you, right? But you can see that a mass, if held in free space and if we let that go, it will start to fall. All right, it will start to fall because that effect was observed by that mass. All right, like was sensed by that mass. That force was sensed by that mass. Okay, just like light was sensed by your eyes. So gravitational field is there, mass is there, so mass can feel the effect of this gravity, and that effect is force, and this force is a vector quantity. So we have just found out a vector field which is actually caused by a vector effect, which is actually caused by the gravitational field. So if, let's say, we are interested in finding out the potential energy, right? We all know that if we have mass on the surface of Earth, potential energy is equals to mgh, mass times gravity times h. If we want to find the potential that exists within this gravity field, then in that case we'll have to take a mass and take it to different sample points, and at each sample point we have to find P is equals to mgh, I mean the potential energy at every point, and then apply those mathematical procedures, and we'll try to find the mathematical expression which is representative of the potential energy within this gravitational field, and that expression turns out to be mgh. Pe is equals to mgh. Okay, so again, whenever there is a field, there is a source. The source of the gravitational field is huge mass. So now we earlier found out the vector field, which is force, and force field, and then we have got potential energy field, which is a scalar field. Okay, so we were given a gravitational field, so collection of scalar field, which is potential energy field, and vector field, which is the force field. These two field, collection of these two effects provided by this gravitational field is collectively, these field word is appended here, so we have got gravitational field. All right, otherwise gravity is nothing but an event, because gravity is present here, present here, present here. Gravity is present everywhere within this bounded region, just like light was present everywhere within the, but that gravity which is present everywhere is not a function of time. Oh, sorry, it's not a function of space. The force experienced by a mass within this gravity field is a function of position. Okay, and the potential energy stored within each mass within this gravity field surrounding this earth is something which is depending upon the height or the position. Okay, so gravity is present everywhere, but its effect is different at everywhere. And if the effect is different everywhere, it means that there is a sense of getting a function. Something, if it is constant, then you say that gravity is 9.8 meter per second. Acceleration due to gravity is this. This is a constant thing. Okay, but if you have got a function like this function, this function potential energy is a function of height h, which is a position, in other words. So now this has got a sense of function, this has got a sense of function, and a mathematical definition of field was field is a function of position. So these are fields, this is constant. So collection of all the field effect caused by the gravitation is known as gravitational field. That's it. Okay, and by the way, this one is a good example. This vector field belongs to force field type of vector field, because there is no sense of motion. If this mass is held there, it is just experiencing a force. But if we would let it go, it will start to move in this direction. And if we are interested in the velocity of this mass, then we can write an expression for velocity of mass at every point. We take the sample velocity at every point, apply the mathematical procedure, end up with this expression. And now this expression is again a vector field, but this vector field belongs to flux density type of vector field. I hope I have made myself very clear. Okay, so all right, so okay, how about this electric field? Electric field, there should be some bounded region to qualify as a field. Okay, the cause of the source of that field is a charge, static charge which is not moving. If there is a charge, or I should say like this, if there is a static positive charge, it defines a bounded region in which its presence can be felt. So this field surrounding this static charge, which is not changing position. Static means not changing position, and number two, not changing value. I mean, if it is 1 coulomb, it is 1 coulomb. It is not changing to like 1.5 coulomb. If these two conditions are met, then this is known as static condition. So this charge is a static, stationary, static. So it is defining a field which is known as E field, electric field. And we will be trying to figure out several effects of this field, and those effects will either be scalar effect or vector force effect or vector flux density effect. Similarly, if we have in space a negative charge, stationary, not changing value, not changing position, then it will define a volume around it, a three-dimensional space in which its presence can be felt, and that field will be known as electric field, because electric charges are there. And we will try to find out several effects of the presence of this charge. Okay, so electric field should be clear now. Okay, so if the charge is moving, any charge, positive or negative, let me take this positive. If a charge is moving with constant velocity, I'm talking about velocity, not speed, because velocity also takes into account the direction. If it is moving with constant velocity but not changing, not changing its value, then this charge surrounding this charge is a field which has got an electric nature in it and a magnetic nature in it. So the magnetic field is represented as H field, unlike electric field which is represented with E. Magnetic field is represented by H. So this charge which is moving with a constant velocity and it is not changing its value, either positive or negative, it does not matter. The charge can be positive or negative as long as it is constant in value and moving with constant velocity, meaning it is not even changing its direction, it is just moving in one direction. In that field, that charge which is moving with these properties, not changing value, not changing direction, having constant velocity, this charge has got a field surrounding it which has got both components, electric field components and magnetic field component, meaning that this charge can affect any charges with which it encounter. It will affect those charges, or either pull or push, and it will also affect any magnetic field which it can encounter while moving. If there is a bar magnet, it can push that bar magnet away or it can pull the bar magnet towards it. So, but generally if a charge is moving with constant velocity, the H, the magnetic field component, is higher. The E component is it's not negligible, but there might be certain cases in which E component is higher. So we can say that a charge moving with constant velocity and not changing its value constitute a field surrounding that itself, which is of electric and magnetic nature both. Okay, but what if, so it is actually constituting an electromagnetic field, where the component of H, magnetic field, can be higher or E can be higher. But what if a charge is moving with time dependent velocity, meaning it has got acceleration, or if it is moving with constant speed but changing direction, meaning changing velocity, meaning acceleration is there, and its value can change or cannot change, right? That field, or you can say that if it is moving with time dependent velocity and it is not changing value, its value, or it is moving with constant velocity, two cases, moving with time dependent velocity and not changing value, or if it is moving with constant velocity, just like this case, constant velocity and changing values, changing the values, or it is moving with time. The third case would be, or if it is changing with time dependent, if it is moving with time dependent velocity and also changing in its value. In all these three cases, there will be a field surrounding this charge, this moving charge, which will be of pure electromagnetic nature. And one more thing which will be different in this case as compared to this case, that this field will be radiating. It will not be bound to certain region. It will radiate. It will start to radiate, and how it will radiate, it depends on the velocity and everything. So we are not going in that detail, but you should all know that whenever there is a field, there is a source. Okay, So if there is an electric field, there is a source which is a static stationary charge. If there is a magnetic field, the source can be a bar magnet, but we are not interested in that kind of sources, because they have got very limited applications, and they will not serve the purpose of studying this electromagnetic field, which is very generic. So we are not interested in that. So if a charge is moving with constant velocity and not changing its value, it will generate a field. That charge will be the source of the electric field and magnetic field surrounding it. And if a charge is moving with either with time dependent velocity and not changing its value, or constant velocity and changing its value, or both, it has got an acceleration and also changing its value, it will constitute, this charge will constitute a field, or we can say that this charge will be the source of the field, which is of both electric and magnetic nature, or in other words, that field will be electromagnetic field, and plus that field will start to radiate in space. All right, so we have discussed all these three. Maxwell's equations, electric field, magnetic field, and electromagnetic fields, all are succinctly defined by, comprehensively defined by Maxwell's equations. There are 4 equations which we will study throughout this course, and in essence we should say that, I want to say that study of EE382 electromagnetic field is essentially study of Maxwell's equations. So there are 2 approaches to study the Maxwell's equation. One is known as inductive approach, the other is known as deductive approach. Inductive approach is the one in which you take general basic physical experimentation and try to develop those experimentation in mathematical form, and then finally study the Maxwell's equation. That is inductive approach, and this approach is adopted by your book, and personally I like this approach. And there is some deductive approach in which the books give you all the 4 mathematical expressions, all the 4 Maxwell's equations in chapter number 1 or 2, and then they study the special cases of those effect, and then they go down to the fundamental physical experiments like Coulomb's experiment and Oyster's experiment, and so on and so forth. So I know I took a lot of time on this lecture, but I wanted to complete this. I hope you would be able to grasp this course, this lecture, and there are 2 points which are left, 11 and 12. I will try to cover that in the next week, inshallah. So see you in the next week. Thank you. Assalamu alaikum.